Okay, Philippe and Bob, many thanks for inviting me to give this keynote lecture online. I'm really honoured to be allowed to do that. I apologise for not making the pilgrimage to Austin in the flesh to be there with you all, but I think I put this down to the wisdom of increasing age. I hope that my talk will be of some interest to you all, but please don't raise your hopes too far in terms of lessons learned in the title. My talk is going to follow the framework of the written version, starting with my early career reflections, getting into offshore geotechnics, then highlighting 2 or 3 technical topics where significant development has occurred in the last 2 decades, some of which I've been quite closely involved with. As part of these, I'll reflect on the main incentives for new or evolving design guidelines. I'll then return full circle to offshore development in Australia, which is where it really all started for me. Early in my career, I was blessed by having some exceptional mentors, and I've picked out some of these here. John Burland was my first boss after graduating from Oxford, and under his overall leadership, I learned my first real soil mechanics. When I undertook a PhD on pile foundations, Peter Roth was my supervisor, and he embedded lifelong learning skills of clear thinking, although I guess I'm starting to lose that now, and precise writing. At Cambridge, during and subsequent to my PhD, Andrew Schofield was my professor, reinforcing my understanding of critical state soil mechanics, but of course, passing on to me his missionary zeal for centrifuge modelling. Closer to home, in Austin, Lyman Rees deserves special mention as he was my first overseas host in 1978, immediately post-PhD. On a warm summer day, I suspect I was the only person lazing on the grass at Barton Springs, wading through a pile of his PhD students' theses. In respect of offshore geotechnics, I think that Don Murph, originally Houston-based with Exxon, has pride of place. Through my career, I've kept finding old papers from Don and his colleagues that predate similar work of my own, generally simpler and more elegant. This photo shows him receiving yet another OTC Hall of Fame award. I'm still in contact with him though, but I rather prefer this picture. He's still competing. This is at his 80th birthday, still competing nationally in masters competitions and winning. So definitely both smarter and fitter than all of us. My first interactions with the offshore world were through the ESAC, Effective Stress Axial Pile Capacity in Clay project, a JIP led and managed by the irrepressible, if troubled, Ben Murphy. Peter Roth at Cambridge invited me and Jon Steenfeldt to help on various aspects of that project. I think we learned a lot, but perhaps the most long-lasting contribution was my rather poor compromise offered by the OTC paper with Ben Murphy. At that time, Don Murph invited me to join the API Geotechnical Resources Group, which later joined with the current ISO Foundations Committee. I soon learned something about the politics of design guidelines, in particular how science must often take second place to pragmatism. If it ain't broke, don't fix it. But then came the challenges of the North Franklin platform on the Northwest Shelf of Australia. Technically fascinating, with piles free-falling through calcareous silts, sometimes up to 100 meters, but also a vehicle of introduction to a who's who in offshore geotechnics at that time. Through a sequence of in-person meetings, no virtual meetings in those days, and workshops of the geotechnical experts representing each operating partner in the Northwest Shelf project. A second transitional project, transitional in the sense of linking Cambridge and Australia, took place during my final year before migrating to Perth. This was the strut strengthening systems developed for SO Australia's first generation oil and gas platforms in Bass Strait. The effectiveness of the struts rested on the lateral stiffness of the piles pinning them down to the seabed. Exxon, Don Murph again, but also his colleague Brian Wesselink, funded 2 separate sets of model tests. One set at centrifuge scale in Cambridge, which I led, and one at small field scale in a pit in southeast Australia. In the final, I remember this project so well because in the final throes of reporting the centrifuge model test data, just as I and my family were due to fly out to Perth, my PhD student, Ian Nunith, working with me on the tests, ended up in hospital with a kidney stone, leaving me solely responsible for carrying the can. To my knowledge, the outcome of that project was the first PY formulation linked directly to the cone tip resistance. The form of the relationship was fitted to the combined data from the 2 sets of model tests in a form that is very similar to much more recent recommendations that I shall refer to in a moment. Before turning to some examples of developments in design that have occurred in the last couple of decades, I want to reflect on some of the incentives for change. An obvious driver is lack of conservatism, although it's often difficult to gather convincing data for this unless actual failures occur, as of course they do from time to time. The introduction of new technology needs new design approaches, and this has occurred in deep water developments, for example, with approaches needed for suction caissons, mud mat foundations, anchoring systems, and so forth. More recently, offshore wind turbines have necessitated improved design approaches for the large diameter monopiles used for the foundations, and the global spread of the offshore wind industry has brought particular challenges for much more difficult seabed conditions than found in the waters of Northern Europe. Turning to some specific advances in the last 20 years, one of the most, in my mind, important has been the improvement in design approaches for piles in sand. Work by the Imperial College team, led by Richard Jardine, including Barry Lahan, and subsequent statistical analyses by many others, as presented in this conference, has finally enabled a unified CPT-based method, main text method for foundation design for axial capacity. This method importantly takes account of friction degradation and the area ratio of the pile, and is based solely based directly on being proportional to the cone tip resistance, without needing to introduce derived parameters such as friction angle or relative density. Cone-based methods have also been proposed for the lateral response in sand. The formulation for calcareous sand proposed by Elio Novello in 1999 builds on that from the Bass Strait project, with a power law PY response and mobilized lateral pressure proportional to the 2/3 power of the normalized cone resistance. A similar expression has been proposed more recently for silica sand by Surya Santana and Lahan, although I think still needs careful validation from field test data. Applications such as riser fatigue and the operational response of offshore wind turbine monopiles merit particular attention on the small displacement response of piles. Scientifically, this is best related to the small strain shear modulus of the soil, with the tangent PY curve, PY gradient around 5 to 7 times G0. Note, however, the very high curvature that we see, with the secant PY gradient reducing rapidly as the displacement increases. It's interesting how closely matched these two PY curves recommended for different materials in clay by Jean-Jean and in sand by Bird et al. For the PISA project. But they show very similar characteristics. Of course, the question always arises as to whether simple beam column PY approaches can truly capture the complex and evolving strain patterns of laterally loaded piles, especially for low aspect monopiles, where the operational response shows considerable bending of the pile and very low strains in the lower part, By contrast, at displacements approaching failure, the pile rotates essentially as a rigid body. This transition is nicely illustrated from the work of Zhang and Anderson. However, from a practical point of view, load transfer analysis remains a practical design tool for the bulk of design studies. Deepwater systems have necessitated a whole new set of challenges and new design approaches. Developments include multiple subsea shallow foundations and different sorts of anchoring systems that range from piles to suction caissons, plate anchors, torpedo anchors, etc. Each new type of technology requires studies to establish design approaches. I'm going to focus on a couple of these where I was involved in industry-sponsored projects to develop design bases. The first of these is connected with deepwater subsea foundations. These can range in size from small sub 10 meter dimension foundations for pipeline termination points or inline T's and so forth, or up to quite substantial sizes, like the main manifold at the deepwater Jansz field offshore Australia's northwest, which is 30 meters by 40 meters and weighing close to 1,000 tons in air. Bearing stresses are relatively low, but lateral and torsional loading can be very high because of the connecting flow lines. Large foundations such as these need to be restricted from movement, while on the other hand, there's an increasing trend to allow smaller foundations for plets, etc., to slide as the attached pipeline expands and contracts. So a very effective way to prevent a subsea foundation from sliding is to include gravity-installed pin piles at each corner. Such so-called hybrid mud mats need a design basis. And a simple approach was developed by BP and Subsea 7, who funded a series of model tests at UWA supported by analytical calculations. BP also undertook detailed finite element modeling of the problem. Here you can see the centrifuge model mud mat, which had short skirts and piles at each corner. These were installed in flight to replicate field conditions. Tests were conducted with mud mats without piles and also mud mats with pin piles under complex three-dimensional loading. I'm just going to mention one outcome of that project, which is a simple analytical design basis that was developed with separate consideration of the mud mat and piles as two independent foundation systems. The pile group capacity was evaluated analytically, and the mud mat capacity was assessed using a simplified design framework published by Feng et al. In 2014. The load sharing between mud mat and piles was optimized using these beta factors here in order to ensure that failure occurred simultaneously of the pile group and the mud mat, which is then an optimal solution. And so the simple spreadsheet implementation for design showed really quite close agreement with serviceability limits evaluated using finite element analysis. It's always rewarding to see research developments being applied in practice, and this was certainly the case for hybrid mud mats, with projects incorporating pin piles developed offshore West Africa and in the Gulf of Mexico soon afterwards. Shown here is a schematic of one provided courtesy of Subsea 7, with the mud mat laid in line with the pipeline, here without any piles, and then the pin piles installed by gravity using a clump weight to assist, and then locked in place robotically. It's quite a complex offshore operation, but videos shown that it all worked extremely well. I want to turn now to anchoring systems, and in particular a similar pre-qualification study involving complementary physical and numerical modelling together with analytical treatments. This was undertaken by Exxon at UWA for permanent Sepler moorings, suction-embedded plate anchors, which they wish to use for permanent moorings as opposed to temporary moorings offshore West Africa. The main aspects considered by the study were enhanced embedment loss during keying, operative bearing factors based on a bearing factor times the strength at the initial embedment depth, multiplying by the total plate area, including the keying flap, and the subsequent effects of cyclic loading. And you can see here the little Sepler model for the centrifuge tests compared with the prototype. Of course, among the outcomes of that study was clear evidence that the keying flap, as originally designed, was completely ineffective. If anything, it was hinged in the wrong direction, since during keying, the rotation of the anchor prevents opening of the flap because of the high soil pressures acting on the back face of the cap down here. This outcome has now been accepted in modern Seplers, where I think the keying flap is now, has now been done away with. Just to show one example outcome of the centrifuge model test, this illustrates the Sepler response under cyclic loading. For both sustained and cyclic loading, it was found that there was an increase in capacity under moderate levels of sustained loading because of the benefits of increasing capacity because of consolidation. However, at a maximum load of around 75 to 80% of the monotonic failure load, accelerating movements will lead to failure. So the resulting design bearing factors are taking into account all aspects of embedment loss and consolidation and the effect of cyclic loading reduces from the ideal plate factor of about 14 down to between 7 and 7.5. Subsequent to that work, further studies on plate anchor performance have been undertaken extensively by Yinghui Tian, as presented already at this conference. He showed that the pad-eye loading angle could be optimized in such a way that the anchor, even Seplers, could be made to dive initially as the mooring load was increased. This has the potential to double the holding capacity, although ultimately, of course, this is limited, or probably limited, by the capacity of the mooring line. So I want to end this presentation by returning to reflect on developments in Australian waters. The nature of the calcareous sediments, generally uncemented silts at shallow depth, overlying calcarenite, weakly cemented limestone, if you like, has created challenges at the development of new design approaches. Routinely now, axial load on pile foundations is carried by grouted inserts embedded in the underlying limestones, with design parameters generally correlated to the profiles of cone penetration resistance, but with detailed quantification through monotonic and cyclic CNS testing. The cyclic loading response of the cemented interface between insert and calcarenite has received particular attention, with specialist axial load transfer software developed, again with parameters quantified through CNS testing, but using the cone resistance profile to interpolate between tests. In a typical design, cyclic loading can reduce the load transfer in the upper half of the pile to residual conditions. Successive high design storms gradually fail the interface, and then subsequent smaller storms degrade the failed interface down to the residual level. And it's not untypical to look for the upper half of the pile or half of the pile soil interface to be reduced to residual conditions during the lifetime cycle of storms that will be seen. So as part of the process of understanding the cyclic loading response of uncemented calcareous silts, full flow penetrometers such as the T-bar and ball penetrometer were developed. These allow soil to be remolded in situ through successive penetration and extraction cycles of the penetrometer. A comparison is shown here of the monotonic penetration resistance of a T-bar with that of a cone in the field. And you can see that they track very closely together, even through quite strong layers. The T-bar extraction resistance is lower because of the partial remolding during the initial penetration. And subsequent penetration and extraction cycles that may be done over a depth interval of maybe half a meter show a gradual loss of resistance. In this case, over 10 cycles, the resistance reduces to about a quarter of the initial value. But in some of the calcareous silts, that sensitivity can be as high as 10 or more. Grafted insert piles did not always go as planned. And in the first platform designed in this way in the late 1980s, the Goodwin A platform, unexpected crushing of the driven primary piles occurred. So the primary piles were just over 2.5 meter diameter with a relatively thin wall for that time, a DNT of 59, although that sounds substantial in the modern context of monopiles. 16 of the piles suffered severe distortion. You can see the profile here with relatively soft silts with a couple of small layers, but the damage was done by this deep 75-meter layer of very strong cemented material. So the damage starts at that hard layer, and then as the pile is driven the remaining 40 meters or so to the underlying calcarenite, we see the pile completely closing into a peanut shape. This process has been referred to now as extrusion buckling. It's well understood, but quite complex to analyze. It's interesting that projects such as these in the Australian offshore, and there have been quite a few of them, combine both extremes of free-falling piles in the upper layer that has to be controlled, together with potential tip damage and extrusion buckling as a result of embedded stronger layers. Challenges indeed. So, in summary, have we learned anything? Indeed, I think we have, and it's been great fun in the process. In terms of underlying approaches, I think the quality and applicability of in-situ testing stands out, both in terms of the equipment and testing protocols that have been developed and the move towards direct application of CPT data in foundation design. And I think that's a challenge for the next few years, is to broaden that application to new design approaches, or new systems, if you like. The power of combined physical and numerical modeling is immense and deserves wider application in day-to-day design. Detailed modeling can be quite expensive, but failures are much more expensive. On a final note, I feel my career has come full circle, starting and ending with problems associated with free-falling piles, from North Rankin to recent events in Asian waters. But also, of course, the potential for tip damage, such as at Goodwin and in new territories, where offshore wind fields are being developed and sediments that potentially contain boulders or other localized hard zones. I think this has come very much back to the fore again, given the very high D-on-T ratio of large diameter monopiles, where I've always felt designers were skating very close to the edge. I think problems such as pile run and tip damage are avoidable. Mechanics are straightforward, although quantification requires proper investment in engineering analysis if costly failures are to be avoided. And I think the developers and investors need to be aware of the need to invest properly in engineering studies to avoid such problems. So, in finishing, I would like to acknowledge all my many colleagues throughout the world, but particularly students and colleagues locally at UWA and in the local office of what was Advanced Geomechanics and is now FUBRO, have contributed to my enjoyment of my career and of course some of the many developments that have occurred during that time. So with that, I thank you all for your attention. Thank you very much.